Assalamu alaikum wa rahmatullahi wa barakatuh. What's up, guys? So, today we're going to be doing a past paper walkthrough of paper 6 since for Igcse students there's going to be the paper 6 physics exam on the 19th of May. So, I figured I would make this video and we're going to be going through May-June 2025 variant 6-2. Okay, I actually did this paper while I was recording, and then I figured that the voice was very distorted, so I have to remake this all, but no worries, we'll go through it. So this is paper 6, and then so it's for 40 marks, and let's go to question 1. Okay, a student determines the internal diameter d of a test tube. The apparatus is assembled as shown in figure 1.1. so there's the stand, there's the water, there's a test tube, and then there's this h over here which we have to figure out what that is. The student fills a measuring cylinder with water up to the 100 centimeter cube mark. He pours some water from the measuring cylinder into the test tube. Let's say the student is like Jack. Okay, let's take a really niche name. Jack pours some water from the measuring cylinder into the test tube. Okay, so this is the full size diagram of the bottom part of the test tube. So this is basically the full size diagram. Okay, the h. On figure 1.2, measure the height h in centimeters to the nearest millimeter. Okay, so to measure the height, you take from this point all the way. Okay, wait, no, not from here. You take the point from this all the way till here. Okay, or basically in simple terms, you take from here all the way to here. Now you may be like, okay, why are they asking in the nearest millimeter? That may be because you may get the answer in 3.35. okay, when you get in 3.35, when you round this to the nearest millimeter, it will be 3.4, because 1 centimeter is 10 millimeters. So if you look at this position, which is basically 1 centimeter is 0.1 millimeter, and it will be over here, so it will be 3.4. so this will be 3.4 centimeter. Okay, and then you have to record your result in the top row of table 1.1 on page 4, which is over here. So 3.4. Then this part, figure 1.3 shows the volume of water remaining in the measuring cylinder. Okay, so he poured some of the water into the test tube, and then the remaining in the measuring cylinder is this. So you know that this shaded area, it shows the how much volume is left. So that means from here all the way till here, this is 80, 81, 82, 83, 84, 85, 86, 87, 88, and then 89 over here, right? And then this is 89. Now a quick thing you should know, it I'll remove all of this. Okay, you need to know this. Okay, you measure and read the scale from this part. You don't take this. You may think that this is maybe 89.9 or 90, but no, you take it from here. So this will be 89 because of the meniscus rules. Okay, so yeah, that's really important to keep in mind. Then calculate the volume V of the water poured into the test tube. Use the equation V is equal to 100 minus R. Now you take the reading, you know R is equal to 89. We also have to put it over here, 89. Okay, now to calculate V, or basically the volume, you do 100 minus 89, which is 11, and then you put it here. So you have gotten all of these marks. Okay, it's really important that you get this correct, otherwise your the consecutive questions will then get you the wrong answers as well. Okay, so you have done this. Now basically the student adds more water from the measuring cylinder into the test tube. He measures the new height h of the water in the test tube, measures the new reading R of the water remaining in the measuring cylinder, calculates the volume of water V in the test tube, repeats the procedure for 3 more values of h, R, and V. The student's results are shown in table 1.1. So basically he repeated like 4 more times, okay, over here with new values of h, R, and V which he got. The student's results are shown in table 1.1. It is important to avoid line of sight, or basically parallax error, when reading the scale of the measuring cylinder. Describe how such errors are avoided. Basically, the most simple marking scheme point is that you read the scale at right angles or perpendicularly. What I mean basically perpendicular is that example, this is the measuring cylinder and this is your eye level. It has to be perpendicular or right angle. Okay, so there are basically rules on how you read. Like example, when you're reading the volume of water here, you have to keep in mind the meniscus rules, and same over here, you have to read the scale at right angles or perpendicularly. Then we go to the graph. Okay, so first things first, you have to get the labeling correct. Okay, so we know that the volume will go on the y-axis as they have told, and the height will go on the x-axis. You have to get this correct, because if this is the other way around, your whole graph will be wrong and your 4 marks will be gone. Then start your axis at the curve. Okay, one second, let me remove all of this. Yeah, okay, so yeah, start your axis at the origin. We have to start from here, 0 0, and draw the best fit straight line. Okay, now it's really important that you have to draw the best fit straight line, meaning you have to draw a line either like this. A straight line can be all of these, all of this, all of this. Okay, all of these are straight lines. If they ask you curve, you have to draw something like this, maybe like this, maybe like this, maybe like this, something like that, a curve. Okay, but if they tell you, okay, if they don't tell you, because in this paper most of the stuff has been given, draw the best fit straight line, they have told you what type of line. If they don't give you anything and they just say draw the best fit line, then you have to look at the trends. If it's a curve, if it's a curvy trend, then you draw a curve. If it's a straight, if the points are coming like adjacent to each other and you think you can make a line that's straight and it passes to at least 2 points, then yes, you draw a straight line. Okay, so now let's do the question actually. So now we have to look at the readings. Okay, we have let's look at the table. So we have to take H over here and V, right? So H and V. Now we know from H it's still 13.6 and V maximum is still 47. So we can take a suitable scale such as 10, 20, 30, 40, 50 and 60. It's every 10, like 1, 2, 3, 4, 5, 6, so 60. So 47, the maximum value of volume, which is 47, it will come over here, which is more than half of the page. It has to half of the graph. It has to be more than half of the graph. And same for that, the highest value is 13.6 here. Wait, 13.6. So we can take this over here. Over here we can take it till 16. So 2, 4, 6. Well, let me remove all of this so it's more easier. Okay, but I'll remove this whole graph. I'll draw it again. Yeah, okay, now since we have the scales sort of, because 13.6 will be over here somewhere, maybe this is 13, so 13.6 will be here, 13.6 will be here, so the graph, it covers more than half of the graph. Okay, now we go to the values. So it's 3.4 and then 11. Now for the volume it may be easy, because you know that this is 1, 2, 3, 4, 5, 6, 7. Wait, let me remove all of this unnecessary stuff so that it's easier for you guys. Okay, so yeah, 11 will be somewhere around here, right? 11. But how do you know where 3.4 is? Okay, now for some of you, you may think, okay, this is 3 and then it's point, so this will be 3.2, 3.4, 3.6, 3.84. Perfect, you know that. But what if it's a bit smaller, the scale, right? So the easy way to know this is that you do this. You do 4 minus 3. Let's take between these 5. Okay, these 5 blocks. You do the bigger minus smaller value, which will give you 1, and then divided by the number of blocks between 4 and 3, which is 5, meaning which will give you 0.2, which means that each block is 0.2. So 3.2, 3.4, 3.6, 3.84. So this over here, if this is 11, then this will be 3.2 and then 3.4, which is over here. Perfect. Then we go on to 5 and 16. So 16 will be somewhere around here. This is 11, 12, 13, 14, 15, 16, and then we have 5 will be in the middle, or 4.2, 4.4, 4.6, 4.8, and then 5. Then we have the 7.6 and 25. So 25 will be here, this is 21, 22, 23, 24, 25, and then 7.6 is over here because this is 7, right? And then 7.2, 7.4, 7.6. Then we have 10.3 and 36. Okay, it's be careful that you do this one, these two, okay, not the R. Okay, then 10.3 and 10.3 and 36. Okay, now 36 will be obviously over here, 31, 32, 33, 34, 35, 36. But 10.3, we know that this is 10, so 10.2, and then 10.4 is over here, so this will be 10.3 in the middle, because 10.3 will come between, in the middle of 10.3 and 10.4. And then finally we have 13.6 and 47, the highest ones. So 45 is over here, so 46, 47, and then 13 is over here, so 13.2, 13.4, 13.6, and that's the last point. Now it's a best fit line, so you start from here. Now since I don't have a ruler right now, I'll just make an approximate line of how it will look like, something like probably like this, right? At least 2 to 3 points are covered, and you can obviously extend it, and it has to be a straight line. Okay, no curves like this over here. I've just started approximately. Okay, then we come to the next part. Determine the gradient G of your line. Show all working and indicate on the graph the values you use. Okay, now you need to know that for gradient, the formula is always y2 minus y1 over x2 minus x1. So basically you use the triangle method, because for gradient it's always area under the graph. So example, if I take maybe this point over here, okay, this point, and I take maybe this point over here, then what you do is that you draw a straight line like this to the, I'll try my best of abilities, and one over here. Okay, yeah, that is not a straight line. Yeah, I guess. Okay, we're gonna remove this. So yeah, you have drawn this triangle. Okay, now what you do, you take okay, I'll remove this. So now let's take these points. Okay, so this over here is your y2 and x2, and this over here is your y1 and x1. So this is like the small, like this, the lower area is your y1 x1, and your higher area is y2 and x2. Okay, so this point over here, if you can see, this is 50, so your y2 is 50. So we take 50. Well, let me remove all of this random stuff. So your y2 is 50, and your x2 is, if you look, it comes over here, which is 14, 14.2, 14.4, 14.6, 14.8, 15. So it's exactly 15. So it's 15. Yeah, your x2 will come here 15. And then your y1 over here, y1 is, if you look over here, y1, that's 1, 2, 3, 4, 5, 6. That's 6. And then your x1 is 2. So if you put that in to a calculator, I'm going to use a calculator. 50 minus 6 is 44 divided by 13. So it's around 3.38, something like this. Okay, now this may not, your answer obviously will be different, because also my graph is really like not that perfect, not accurate. So you might get a different answer. It's fine as long as you have your as long as your labeling is fine, your graph is straight line, it covers 2 to 3 points, your scaling is correct, then it's completely fine. Then we have this. The internal diameter d of a cylinder is given by the equation d this, okay, where k is 1.13, okay. Also in this question you don't have to give a symbol, but you have to show this working because it says show all the working, okay. So yeah, the internal diameter d of a cylinder is given by the equation this. Calculate d. So you know k is 1.13, and then you just plug in your g, which you got over here, and you get your answer. And centimeter is already given, so you don't have to put a symbol, okay. Okay, suggest one reason why your calculated value for d is only approximate. Okay, it's approximate because look, where did you get your the d from? You got it by using g. Where did you get your g from? By using the graph, okay. So you got your value for d basically from the graph, okay. And what is your graph? Is your graph accurate, completely accurate? Is it approximate? Yes, your graph is approximate because the gradient of the line or the graph is approximate and not accurate, so that's why, okay. So yeah, okay. Okay, so moving on to question number 2, which is usually regarding maybe the electricity chapter or maybe regarding reflection of light, but in this case it's about electricity. So a student investigates a light dependent resistor, LDR. The student assembles a series circuit consisting of a power supply, a switch, a 470 ohm resistor, and an LDR. So a figure 2.1 shows part of the circuit that the student assembles. So you can see this is a series circuit. Complete the circuit by adding the correct symbol for an LDR between Y and Z. So I'll just remove all of this. Okay. Choose from the list provided in fig 2.1. As I said, even in this question they told you the best fit straight line. They usually don't even tell that. And over here they have told they have given you a list. So you know that LDR stands for light dependent resistor, and these two, they're basically diodes. So if resistor is usually like this and this is a diode, so you can immediately cross this out. And then you know that it's a light dependent resistor, meaning light is shining onto it and not coming outside of it, it's not being emitted. So this is also wrong, and so this one is the correct option. And then you have to draw it in series like this. Okay, BI. The student he closes the switch, connects the voltmeter across the 470 ohm resistor, records the reading on the voltmeter, and then opens the switch. On figure 2.1, draw a voltmeter connected to measure the potential difference across the 470 ohm resistor. So this is the 470 ohm resistor, and then voltmeter is always connected in parallel. So we'll draw it like this. Okay. So the voltmeter reading is shown in figure 2.3. Record the voltmeter reading Vxy. So this is 0.8 because this is 0.1, or we can use the same thing as I told before. 1 minus 0 is just 1, and then divided by 10 gives you 0.1. So each step is 0.1. So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. So that's 0.8. Now the current I in the circuit is calculated using the equation this. We know that I is equal to V over R. So resistance is given and the voltage we found out over here. Use your voltmeter reading in BII to calculate the current I. So we know that the voltage is this, the resistance is this. So now we need to find the current, and current is voltage over resistance, as they've given the formula over here as well, though they you usually don't get that in paper 4 or paper 2. So it's just 0.8 over 470, which is 0.0017 ampere. And just write the symbol over here. The symbol is really important, okay. The student closes the switch, connects the voltmeter between points Y and Z, records the voltmeter reading VYZ, opens the switch. So basically it's the voltage being supplied between these points and these points, okay. So the resistance is basically voltage over current, and the current stays same because it's a series circuit. So whatever answer you got here, you're going to be using that, okay. So voltage is this, current is this, 0.0017, and so resistance will be 2.2 over 0.0017, which is actually 1294 something, but since it's 2SF, because if you look at the previous values 2.2, 0.0017, and then 0.8, all of these seem to 2SF, so that's why if you do it to 2SF you'll get 1300, which is also correct. Then the student, okay, now the student does the same experiment but with a different apparatus. The student covers the LDR with a piece of card and repeats the procedure described in B and D. So it's the same experiment but with a card over the LDR. So if this is the LDR and then it's like this, there's a card over it. The example, this is a card, so there's a card over it. Okay, let's just scrap that for now. So they repeat the experiment, and now they want to calculate the resistance of the LDR in the dark using this equation. Okay, 470 times yz over vxy. Now vyz is this and vxy is this, so it's really important you don't confuse them because you'll get the wrong answer. Then when you do 470 times 2.9 over 0.15, you will get 9086, and then if you do this to 2SF, you will get 9100. Now the student removes the card from the top of the LDR and slowly lifts it vertically upwards away from the LDR until the card is 30 cm above the LDR. The student observes and records the readings on the voltmeter across the LDR VYZ as the card is raised. So now you can see over here that as the distance, if it's 0, 5, 10, 15, 20, 25, 30, you can see at 0 it's 2.9, at 5 it's 2.5, at 10 it's 2.4, at 15 it's 2.3. So as the distance is increasing, as the distance is increasing, but the potential difference is decreasing. So that means that it's inversely proportional. So when it says describe how the PD across the LDR VYZ changes as the distance between the card and the LDR increases, okay? If the distance is increasing, the potential difference is decreasing. And then if you notice at 20, the potential difference becomes constant. It becomes 2.2, 2.2, 2.2. So you have to describe the whole trend basically. As the distance between the card and the LDR increases, the potential difference across the LDR decreases. Then from 20 centimeter distance, the reading on the voltmeter becomes constant as there is no change. That's it. Then we have F. When the LDR is covered by the card, the current in the circuit changes. Use the student's result from BII, D and EI to show how this change in current affects the value of the total potential difference, which is VXY plus VYZ. Okay, so first it's important to make like a small maybe working here so that you are aware. Okay, we're basically asked to compare before and after the lid. Okay, yeah, so we're asked to compare before and after the lid. Okay, at this point, at this point, this was the point where she added she added the card or the lid. Okay, and then before all of this there was no lid. So if you look at if you notice the before, you will see that before it was 0.8 VXY, since we need to know VXY and VYZ. So at VXY it was 0.8 and then VYZ was 2.2. Yeah. So if you notice here, I've written it already, that before it was 0.8 and 2.2, and then afterwards when you go over here, after she added the lid, it was 0.15 and 2.9. So afterwards it was 0.15, 2.9. We got this from BII and then DI over here, and this was from EI. So 0.15 plus 2.9 gives you 3.05, and this gives you 3. So this was after and this was before, right? So what does that show you? That before the potential difference was less, before adding the before adding the lid of the card, and afterward it was more. So that's how you describe it. When the student covers the LDR with the card, the total potential difference is greater as it increases. This is because with card, the total potential difference is 3.05 after adding all of this, and without card, the total potential difference is 3. And you have to explain it because the student says, it says use the results from the student's results. Okay, so question 3 now. A student investigates the image formed by a converging lens. So it refers to figure 3.1. The student switches on the lamp, places the screen at distance d is equal to 80 centimeter. So this d over here is 80 centimeter, this d, okay, from the illuminated object. Places the lens close to the illuminated object, moves the lens away from the illuminated object until a magnified, inverted, sharp image of the illuminated object is formed on the screen. Okay. On figure 3.1, measure to the nearest 0.1 centimeter the object distance x from the center of the lens to the illuminated object. Basically this. When it says measure, meaning you have to use maybe a ruler, okay? So if we zoom in here, as I said, we have to take from here to here, okay? From this part, from here all the way till here, okay? Now you may notice they say 0.1 centimeter to the nearest 0.1 centimeter. That may be because you make it 4.05 and then you have to convert it to the nearest 0.1, which is this, and then you look at this value, which is 5. So this becomes 4.1. Okay, let me remove this because it was from before. Okay, so that's 4.1, and then we know that we know that this is 1/5. Okay, 1/5. We know that the actual object is always greater than the virtual, which you put it over here, virtual. It always has to be greater. So actual is always greater than the virtual. Okay, meaning the actual has to be times 5 greater, something times greater, right? So 4.1 times 5 gives you 20.5. That's your actual answer. Then the student continues to move the lens away from the illuminated object until a second sharp image, which is diminished and inverted, is formed on the screen. He measures to the nearest 0.1 centimeter again. The object distance y from the center of the lens to the illuminated object, he gets 59.8. Now show that illuminated on figure 3.2, draw a diminished inverted image in the space provided. So diminished means just smaller, and inverted means like the opposite. Okay, so inverted of this would be just inverted would be this, and then diminished would be something smaller, so this. Okay, yeah, okay. Now calculate the value of d. The small this is small d, not the big D is 80 centimeter. So that'll be y minus x. Y is 59.8, and then the big X. Okay, so it's the big X, which is 20.5. So you do 59.8 minus 20.5, which will give you 39.3. So if this part is wrong, then the following parts will also be wrong. Now calculate the value of d from A and use the value of d, and d from B from previous parts to calculate the value of f1 for the focal length of the lens. Give your answer to 3SF. Okay, so d square minus big D square minus small d square over 4 times big D. So big D is 80. It's better you write it first so that you don't get confused. And small d is 39.3, which you got from here. And then you do 80 square minus 39.3 square over 4 times 80. Now it says 3SF. The reason why I didn't just directly write 15.2 is because in many subjects, like in maths especially, if they ask you to show that or give your answer to something in 3SF, you always first have to write the whole answer, okay, and then you round it and write the approximate form is equal to 15.2. You have to first write your full answer and then show that it's 15.2. Okay, so yeah, then the student repeats the experiment with the distance d 100. So before it was 80, now it's 100. The student records the value of x, y, and d. So X is now 18.1, Y is 81.8, and D, which is 63.7. 81.8 minus 18.1 is 63.7. Then step 2, use the same formula over here. So big D is 100. Big D is 100 and small d is 63.7. So 100 square minus 63.7 square over 4 times 100, which is 14.9. Okay, two quantities can be considered to be equal within the limits of experimental accuracy if their values are within 10% of each other. State whether your values of f1 and f2 from previous parts can be considered equal. Support your answer with the calculation. Okay, now just remember this formula for experimental accuracy is this: larger value minus the smaller value over the average of those two values times 100. What do I mean by this? The larger value, what is the larger value between f2 and f1? 15.2 and f2 14.9. So the larger value is 15.2 and then it's minus 14.9. Perfect. But what about average? Average is 15.2 plus 14.9 over 2. Average is basically the mean of those, right? You add all of them, add all of the values and divide by the number of values. So the number of values are 2 over here, and adding both of them is 15.2 plus 14.9 over 2. That's your average. You divide that average under the 15.2 minus 14.9 times 100, which this will give you 1.99%. So the answer is that yes, they can be considered equal because the percentage uncertainty of the two values is 1.99%, which is below 10%. If anything falls below 10% or within 10% or equal to 10%, then yes, it can be considered equal. State one technique to use when doing this type of experiment to ensure that the image on the screen is focused as clearly as possible. It's almost in the mark scheme, it's always this point: moving the lens slowly backwards and forwards. Or it can be also used moving the screen backwards and slowly backwards and forwards if they ask you regarding something for the screen. Okay, this experiment is usually done in a darkened room. Also, this could be another improvement if they ask you using in a darkened room. So yeah, explain how this makes it easier to see when the image is in focus. Okay, in a darkened room, like when it's really less light, the images, I'll not do that. Like example, you have an image here, then you're in a darkened room. The edges of the image, they are more easier to view and observe because the edges of the image are sharper. So that's why. Okay, now finally, obviously, we have the infamous last question, which is honestly the easiest question to score marks in, and I'll explain almost everything. So hot water, I'll remove all of this because it was from before when I was recording, but Okay, hot water is poured into a glass beaker and allowed to cool down for 5 minutes. Plan an experiment to investigate whether the rate of cooling of the hot water depends upon the initial temperature of the hot water. Okay, you need to first identify what the independent and the dependent variable is from this statement alone. You know that the independent variable, IV, is something that influences the other. Like example, if I have fire, and I take ice, this fire is influencing the ice as it melts. So the independent variable is fire because it's not getting influenced by something, but the ice is getting influenced, right? So the ice is the dependent variable. So in this same case, plan an experiment to investigate whether the rate of cooling of the hot water depends upon the initial temperature of the hot water. Depends upon, meaning the rate of cooling depends upon this, meaning the rate of cooling is influenced by the initial temperature of the hot water, meaning the independent variable is the initial temperature. initial temperature of hot water, and the dependent variable is the rate of cooling, because rate of cooling is getting influenced and dependent variable gets influenced. Dependent means it's dependent on something. Independent means it's independent. It's independent of something else. So yeah, the rate of cooling, as I said, they have given you the formula as well, but in many papers it actually don't, so you should know the formula as well. You're provided with a supply of cold water, electric kettle, a 250 centimeter cube glass beaker, a measuring cylinder, okay, blah blah. In your plan, include any other apparatus needed. Okay, I want to ask you guys this. When you want to find temperature, how do you measure temperature? Thermometer, right? And when you want to find time, you use a stopwatch, because those are the essential needs to find the rate of cooling. You're trying to find the rate of cooling, so you need to have a thermometer and a stopwatch, because stopwatch is for the time and thermometer is for the temperature. So that's done. Okay, a brief description of the method, including what you will measure and how you will make sure your measurements are accurate, the variables you will control, a result table, and how you will process your results to reach a conclusion. Okay, also in the result table, you are not required to enter any readings in the table. You may include a label diagram, it's not needed. So I'll just remove all of this so it's more easier for you guys. Okay, okay, let's go to the first things first. Okay, firstly, you always write the additional apparatus, which is stopwatch and thermometer. That's 1 mark confirmed. Now in this marking scheme, when I was surprised to see there was no mark for independent and dependent variable. In most mark schemes, writing independent and dependent variable itself gets you 1 to 2 marks, and so does the additional apparatus. So you're already confirmed 2 to 3 marks out of 7 just writing all of this. That's insane. And then don't even get me started on the control variables. If you write at least 2 control variables, that may be 2 marks. So that's around 4 to 5 marks out of 7 confirmed if you write all of this. Now what are the control variables in this? Obviously the volume of water. Let's say you take one beaker and you take another beaker. Okay, same size, same everything, but one has more volume of water, one has less volume of water. The rate of it will be very unfair for this beaker, maybe this beaker too, because it does not have the same volume of water, so it cannot really compare. You cannot really compare fairly, so you have to control it. Same for the time of cooling. They have already given us a time which is 5 minutes. If you give this maybe 5 minutes and you give this 10 minutes, it'll be unfair for beaker 1, because you're giving unfair timings for both. And then finally room temperature, because in room temperature, if this is maybe 30 degrees and that is 45 degrees, then it will be unfair in the rate of cooling. Then finally the investigation and the method. Investigation is usually 2 marks. Firstly we will take 50 centimeter cube of cold water and measured using measuring cylinder, and put it in an electric kettle and heat it, because this is cold water, right? This is cold water and we need to heat it. So when you want to and you want to take it to hot water, when you want to take it to hot water, you need to heat it with the electric kettle. So you have to mention how much volume of cold water you will take and what you will measure it, which is the measuring cylinder as it's given here over here, and then put it in an electric kettle and heat it as the electric kettle is given over here. Then we will pour the heated water into the glass beaker which they have given, and start a timer of 5 minutes for it to cool, and measure the final temperature using thermometer. I forgot to add here, and you have to heat it to a known temperature like 50 degrees Celsius and measure the initial temperature using thermometer. The initial temperature will obviously be different because that's what we're measuring. That's the independent variable, and you will use it using a thermometer. Then we will pour the heated water into the glass beaker and start a timer of 5 minutes for it to cool, and measure final temperature using thermometer. We will find the temperature decrease by using final temperature minus initial temperature, and we will find the rate of cooling using temperature decrease. And we'll find rate of cooling using temperature decrease over the time. Okay, this as it's given above over there. And then over here till here you have already probably been achieved 5 marks confirmed. And then over here, this is also really easy marks. We will then repeat this with at least 3 more values of initial temperature, because this is just for 1. We need to do this same thing but for at least 3 more in another glass beaker. And it could be, maybe if this was 50, then the initial temperature could be 60, then 70, then 80, as 3 more. The experiment will be repeated. Okay, now this is for 4 values. Then the whole experiment will be repeated at least 5 times. Writing this alone gets you 1 mark. The experiment will be repeated at least 5 times, and the average will be taken for accuracy. Average is keyword over here. Okay, average will be taken for accuracy. Then the table and the conclusion is 2 marks separate. In table, you write the initial temperature over the units. Units are really important, over degrees Celsius. Final temperature over degrees Celsius. And then cooling rate is going to be degrees Celsius over second, because temperature is in degrees and time is over seconds. So that's degrees over seconds. So yeah, correct units, you need to write the correct units. And then conclusion is always this. You always write in conclusion, we will plot a graph of the dependent variable against the independent variable, because the dependent variable, which is this, is always y-axis, and the independent variable is always the x-axis. Yeah, and that's how you get the 7 out of 7. And that is it for this video. I hope you guys enjoyed it. If you guys have any other queries, you may ask them. And if you have any other papers that you would like me to do before your paper, then let me know as well. I hope this helped, and yeah, thank you so much.